discuss. So, okay, let me first, it's the Happy New Year to everybody. This is our your first seminar of 2022, and it's part of our distinguished seminar series here at the Texas A&M Energy Institute. I'm Stratos Christikopoulos. I'm the director of the Texas A&M Energy Institute, and it gives me great pleasure to introduce our first speaker for 2022, Dr. David Miller. I have known David since his PhD days, so he reminded me. So I thought it has been a long time, but I didn't realize it has been that long. So David is the Senior Fellow for Strategic Systems Analysis and Engineering at the National Energy Technology Laboratory at NETL in Pittsburgh since 2009. He did his PhD studies in chemical engineering at the Ohio State University. He served as the technical director of the Carbon Capture Simulation Initiative. He's always been in the simulation and optimization space since his PhD days. So we have, in some sort, we have parallel lives, kind of. And there he pioneered new ways to maximize learning during pilot scale testing to reduce technical risk during scale-up. Scale-up still remains sort of an art rather than a science, I guess, even despite the great efforts of David and his team. And he's currently, and more importantly, leading at the moment the Institute at NETL, the Institute for the Design of Advanced Energy Systems, the IDAES kind of project, which is a major collaborative activity and initiative involving national laboratories and universities across the nation to develop and apply next generation multi-scale modeling and optimization capabilities. My first sort of gut insight when I read this, David, that I thought we have already done this, but I will leave you to demystify this. He's going to present to us today how to optimize a very topical problem, especially for the energy transition space that is very close to our hearts, optimizing innovative process and energy systems of the future via the capability, the predictive capability of this multi-scale modeling and optimization tool. David, it's a great pleasure to have you here. A very warm welcome, and the floor is yours.
All right, thank you, Stratos. Thank you very much for the invitation to come and visit. I wish this was more than a virtual visit. When we rescheduled from last year, who would have thought that we would still be in a travel constrained environment with everything. Let's see. I just got a note that my host has disabled participant screen sharing. So that needs to get fixed before you can see my presentation.
All right. Yes. You should be able to do it now, David. Can you try it kindly?
Yes, it is working, and here are some slides that hopefully you can see.
All set, we can see. Please go ahead. The seminar starts.
All right, thank you very much. And I really appreciate this opportunity to come and talk to you all. So I'm going to talk about optimizing innovative process and energy systems of the future. And I want to start the presentation by talking about what the future might look like, because the future is not today. And what are some of the trends and some of the drivers that make the future different from today? And so, first off, we're all well aware of the big goals of the US in terms of decarbonization, looking at decarbonizing the electricity sector by 2035 and decarbonizing the US economy by 2050. Those of course, will require some pretty significant changes to what we have now. So to help kind of set the stage for that, we can look at this Sankey diagram of energy production from 2020 Sorry, I had a little thing at the top of my screen that's not quite going away, but we'll live with it. Thinking about electricity generation in 2035, decarbonizing that basically means getting rid of some of these blue and black lines that are currently generating electricity and either making those with fossil with CCS or converting to renewables, nuclear and hydro. Of even greater challenge is thinking about 2050 when we're looking at decarbonizing all these other sectors, including transportation, industrial sector, commercial and residential. A lot of the talk around how we might go about decarbonizing these relates to electrification and or hydrogen, which in many cases will cause this electricity generation box to increase in size, potentially increasing the challenge of decarbonizing the electricity sector as that needs to grow. So certainly one aspect of future energy and process systems is changing where we get our energy and how we get energy. Part of that is also reflected in the way electricity is supplied. And so this is a chart of electricity production sort of early, well, about a year ago in Texas that shows the variable supply of natural gas and its contribution to the mix, coal, nuclear, which stays nice and flat, and solar and wind. And the main takeaway from this is as we look at bringing different sources of generation together, there's a lot more dynamics and variability that needs to be accounted for. So the bright side of wind and solar is they don't have any emissions, but we need to have some ability to fill in the gaps with doing that. And so traditional generators or traditional fossil type generation with CCS needs to become much more flexible in order to account for that variability, and new technologies such as energy storage or large grid scale batteries need to be developed and deployed in order to help fit in to this mix. One of the other trends is the need to decarbonize the US industrial sector, while at the same time, the US industrial sector is in many ways expanding as new industries are being developed in the United States, certain supply chains and developments are being brought back to the US, and things are being deployed and growing, and then also the transition to decarbonizing some of these technologies. So for example, I have a picture here of a shell cracker near Pittsburgh that's been under construction and will be starting up soon in response to a great amount of natural gas that's available within the US, particularly kind of more northeast US. There's also the possibility of seeing a lot of expansion for production and use of hydrogen as a new material to be more broadly used as part of the decarbonization strategy that's being developed. One of the other trends to help support all of this is process intensification and modularization. So intensification being, how do we create processes that are smaller and cleaner? There's been a lot of work that's been going on through the Rapid Institute, developing some of these new technologies to the point where they are now ready to be deployed to help support some of the decarbonization efforts, as well as expansion of industry, and also be able to use some of the concepts around modular design to help improve flexibility and decrease costs and enable technologies even as diverse as direct air capture to be able to pull CO2 out of the atmosphere. So lots of new technologies that have been developed as well. If we think about just the CO2 challenge, this is another one of those Sankey charts that shows the total CO2 emissions, and this shows it by sector. So currently, one of the largest contributors of CO2 is electricity generation. And so, thinking about decarbonizing the electricity sector, there's multiple different ways we can go about trying to do that. It includes hydro, wind, solar, geothermal, nuclear, and adding CCS to fossil resources. There's also a lot of other CO2 coming from other sources. So how do we go about most effectively and cost effectively and rapidly decarbonizing electricity generation? There have been a number of studies published about different routes to get to zero emission electricity generation. And one of those that I want to highlight is this one that was published in 2018 that takes a look at the comparative costs for deep decarbonization, whether you have firm low carbon resources such as nuclear, fossil with CCS, and geothermal, or not. And the big takeaway here is without that third piece of the circle, the costs as you start getting CO2 emission limits down very, very low. So trying to decarbonize the electricity grid, the costs of electricity start becoming rather high. Whereas if you have these other resources in place, the costs could grow at a much more reasonable pace. And so the costs become much less. So then the question becomes, how do you employ firm low carbon types of power generation and make that available? What do those systems look like? And so part of understanding that and thinking about that is to understand and look at holistically what an integrated energy and process system looks like, which I depict graphically here in that there's an intersection between different types of thermal energy that is being developed and use of raw materials that can go to power generation. It can go to chemical processes. It can make hydrogen that can be stored. And then that hydrogen could be converted to electricity. That hydrogen could go off to become products. Some of that thermal energy could be stored and used later for power generation. Sometimes that power could be used and stored and used later, or that power could be used for producing hydrogen. And so there's potentially many more connections of different processes in the future than we typically think about now. Now you typically would think about there's a power generator, it makes power. There's a chemical processing plant, it makes products. And there's an opportunity for much more integration potentially that could help resolve some of the challenges, particularly challenges around how do you deploy new electricity generation resources that are only going to be used part of the time in order to fill in the gaps? How do you manage the capital cost associated with that so that you actually want to make that investment? So trying to understand that requires that you think about not only the process, but you think about the process within the context of the broader system that it's going to be operating in. Now, traditionally, we don't do that. Traditionally, we want to design a process, and we think about, for example, a power process, we think about the electricity grid. The electricity grid is an infinite sink for the electricity that I could produce as part of this power plant. Now, traditionally, that was maybe a reasonable assumption, but much less so today. And the grid, typically when people are doing grid modeling, think about the loads on the grid, and then you think about generation being essentially negative loads where you can get power from and move it around to other places. And that kind of approach, again, becomes less relevant as we think about the variability in the future than now. And so we need to be able to think about ways to bridge those gaps. And bridging those gaps is actually a multi-scale problem, is even just thinking about the way the grid operates, there are multiple different scales that are involved that need to be considered. And each one of those scales has different tools and different problems associated with it. And so this is a representation of some of those different decisions that need to be made from an electricity grid perspective, and the time scales across which those decisions are being affected, ranging from milliseconds all the way to decades, and looking out multiple decades. And so on the one hand, there's a real-time operation of the grid, that often includes high frequency dynamics in order to make sure that our AC current has the right frequency. Going up a scale, there's sort of the higher level, dispatch and power flow of how do you turn on different generators, turn them off, and put them together and get all the electrons to flow through the wires in order to meet loads and not have any constraints. One of the challenges with that is, how do you understand where to put new generators and what happens when new loads show up in different places? Thinking about that at that level is much more complex than thinking everything else is going to stay the same, because as soon as you add a new generator, everything's going to change in the way that grid operates. And then at the longer time span still is capacity expansion. And that's essentially the problem of thinking about, in what investments am I going to be making over time in order to meet demand? So there's projections of what demand is going to happen, how demand is going to change over time, what new generators should I be planning for, and starting to do the regulatory work and investment work to get those in place at certain times, and how do I understand how they're going to interact? Because we want to do that in a way that the investments we make are good investments, and we also want to maintain reliability. And then finally, there are energy economy models, which are even larger scale and capture larger dynamics that include things such as supply chains, natural gas supply, potentially flows of CO2 and hydrogen. So across all those timescales with the grid, we have different aspects of the process or the generator interaction, as part of an integrated energy system. So there are aspects of how do we design that process or generator? How do we operate and control it? How do the dynamics of that process work, both now and how do we design it so that those dynamics are going to work in the future? And does it make sense to think about multiple products? So we have multiple revenue streams as we think about integrated energy systems. And then that starts to bring in some of the multi-sectoral interactions and the need to understand what infrastructure is in place now and what future infrastructure needs to be in place in order to realize these types of systems. So for example, interaction with natural gas and fuels, interaction with transportation, as that's potentially electrified. How do we make sure that we have enough electrons at the right places that people can recharge their automobiles, recharge trucks, etc. So lots of different challenges, making for lots of different decisions that we need to be able to make, both now and thinking about the future. So decisions around how do we operate processes? How will we operate processes in the future? How do we design processes? How do we choose among different technology options, especially when some of those technology options are going to be deployed in 5 or 10 years, and we're not quite sure what the world's going to look like? How do we kind of make sure that we've got a reasonable portfolio, and how do we invest in R&D based upon what we think is going to happen and where we think there are gaps or opportunities? So thinking about decision making, there are lots of different approaches to trying to address these problems. So we can have simplifying assumptions and approximations. Those approximations could be very, very qualitative. Those approximations could be linear, but they all provide a way to help narrow down the decision space and make some decisions. We can also use heuristics. Heuristics have been built up by lots of knowledge over the years, very good for making decisions of sort of current technology. But some of those heuristics are based upon assumptions and scenarios that may no longer be appropriate. So some of the assumptions about economies of scale and bigger is better may not be appropriate when you start thinking about processes that start becoming much more dynamic, because there's much more dynamic and very dynamic price variability for some of the raw materials or for some of the energy that's coming into those processes. We can also use spreadsheets. Lots of us like to make really, really complex spreadsheets. Those can be helpful, but there's a lot of hidden information in those spreadsheets, and simulation is another tool, particularly popular among the DOE world, where we've got lots and lots of really big computers that we like to simulate different scenarios, which is great if you can define those scenarios and narrow them down enough that you know what to simulate. And then finally, there's an optimization approach. And optimization is especially useful when you have a large space that you want to understand lots of complex interactions that aren't necessarily amenable to heuristics or approximations, because it's nonlinear and it's more complex than we can immediately grasp. And I'll argue that this is the approach that we need to take in order to understand the potential design and operating space of future energy and process systems. So understanding large and complex systems, we don't want to just simulate. We want to solve these types of problems, and we can solve them. So traditionally, if you think about a simulator, you simulate something, and then if you build a really good simulation, you can sometimes optimize over that, but you have only certain degrees of freedom that you can optimize over. And the size of the problem is typically rather constrained. So conversely, if you can formulate the problem and the challenge as an optimization problem from the beginning, instead of a simulation on top of which you're trying to build optimization, you can potentially solve much larger problems and answer more complex questions. And so this is the idea off of which IDEAS was developed. And so the IDEAS integrated platform starts with the base of an algebraic modeling language, in this case, Pyomo, which is an open source DOE code that's similar to GAMS or AMPLE. It is built on top of Python, and it has access to all of the state-of-the-art solvers, and IPOPT is included as part of the distribution of IDEAS. That's one of the workhorses that we use because it's an open source version. IDEAS includes a modeling framework and a model library that we can use as a starting point to be able to build and understand what different processes might look like. It's hierarchical in that the models that exist within the library, you can abstract to the appropriate level of detail for the questions that you're trying to answer. And the types of applications that we can do with IDEAS include conceptual design, particularly conceptual design using a GDP formulation to help answer questions of how many of this might I want? Either or decisions of choosing between different technologies. And I'll show a couple of examples where we're using the conceptual design capabilities within IDEAS to solve some energy-related problems. We can also look at more traditional plant design and process optimization, and we have support for that. So if you kind of already have a system or a process, you can build a representation of that and model that. We can take that same process and model representation and look at from a very dynamic operations standpoint, including some very advanced capabilities for nonlinear model predictive control, which is represented here by Capresa. We can also look at uncertainty quantification and things such as robust optimization in order to reduce technical risk or understand what that technical risk might be. So the fact that this is all an equation-oriented formulation makes it very easy to include the uncertainty aspects along with the solution for the system. Now, I talked a lot about multi-scale. One of the key tools for helping us bridge those scales are surrogate models. And we have a number of AI, ML, and equation-oriented approaches to developing those sorts of surrogate models that help us bridge different scales or pull in data or information from other sorts of simulations for specific types of technologies. And then finally, at the kind of the largest scale, we have some capabilities around enterprise optimization, particularly optimizing around the grid and understanding how the electricity grid is going to operate and looking at those expansion planning type models, all of which we do in an innovative way where we can look at all the way down to the process scale and understanding the impact of some of the dynamics at the grid and expansion planning scale and vice versa. And then the last capability that we've built into IDEAS is around materials optimization, specifically nanomaterials optimization. And that's another package that can be utilized. So all of this is open source. It's under what's called a BSD license, which is basically you can do anything you want with it as long as you acknowledge where it came from to begin with, kind of license. And we recently published a paper that kind of describes the overall framework in the Journal of Advanced Manufacturing and Processing. The team that is developing and applying this consists of folks from 3 national laboratories, as well as 4 universities. One of the things that we've worked really hard to do is try to make sure that we are taking cutting edge developments from the academic world and pulling those into a framework where those insights and innovations can be applied to solve real problems by this combination of national lab staff and graduate students, postdocs, and faculty at the universities. And now that IDEAS is open source, we are hoping that ecosystem will make it easier for others to use the IDEAS platform to develop their models, and their innovations can similarly be pulled in and have wider deployment and broader impact. We also have a stakeholder board and have done extensive outreach activities. This is actually a picture from FOCAP D back in 2019, before all the craziness happened, when we could all jam into a room and learn about things. And this was a session on kind of an introductory tutorial session, and IDEAS has also won an R&D 100 award. So in the time that's left, I'd like to go through and talk about some examples of utilizing the IDEAS optimization approach. So the first few examples, specifically focus on multi-scale optimization, and then the last example will focus around technical risk reduction through uncertainty quantification and robust optimization. So the first example is, how do we do this process and grid coupling, understanding some of these complex interactions across scales, and what are the different ways we can do those, and why are they important? And so, in general, process world and trying to link high fidelity process models with the grid, the point of intersection in most markets is through what's called a production cost model. And so this is basically the way that the grid is dispatched. So there's a day ahead market where there's a forecast of what demand is anticipated at different times. Different generators bid into that market. That market is cleared. And then the real-time market, which is really 5-minute or 15-minute, depending upon what the actual grid operator uses, then similarly dispatches, tracks the supply and demand, and sometimes causes additional generators to be dispatched when there's a mismatch from the day ahead market to what's actually happening, either because certain generators aren't able to meet their load or demand is different. So what we're doing is using a production cost model to help bridge that gap between what's happening in the grid and what's happening in the process, to be able to look at both from a design standpoint as well as from an operational standpoint. Now, one of the things that's really important to understand is there's a concept called price taker. So in price taker, you can look at what the historical market has been, or a forecast, and do analysis based upon just taking that price. So what that neglects is your impact on what those prices are going to be. And so that's good as a first approximation, but to really understand what the potential is of a new generator, you actually have to couple those, because you're going to have an impact on what those prices are going to be. And just as a real simple example of what that looks like, this is a chart that shows for a given system, this is the renewable production that's both forecast and actual. Here you see that there's a discrepancy, and the locational marginal prices, these are what come from the production cost model. And so depending upon whether you're static or you're looking at what's called an optimized bid, so sort of from a price taker or a market interaction standpoint, those prices actually change, and the number of generators that are online at a given time also change. So changing in how you're bidding into the market affects the market. The things that are going on in the market, and adding something new to that is going to change the market. So one of the projects that we've started up through the Grid Modernization Lab Consortium is called Dispatches, for Design, Integration, and Synthesis Platform to Advance Tightly Coupled Hybrid Systems. It is basically building the framework to be able to bridge that gap between how to do conceptual design of a new integrated energy system with how is it going to impact the market, and how can you design it so that you're taking advantage of what the market needs, or really meeting the market needs. And so there are two approaches that we're demonstrating within this. One is the price taker approach that I mentioned, and that's using historical data, and that historical data is then driving the optimization problem. And then we're also using an approach that takes into account market interaction, using Prescient, which is a production cost model, also built on Pyomo, where we are building market surrogates to then guide that optimization problem. And specifically, using these market surrogates to enable conceptual design, we follow an approach of defining the search space. In other words, what are the hybrid or integrated energy system technologies that you're interested in understanding? We look at the market simulations over a time period in order to understand how different characteristics of that integrated energy system would impact and affect the overall grid through the production cost model. train those surrogate models, and then use those surrogate models to define and solve the superstructure to determine the optimal design. From those best candidate solutions, and we simulate those and their detailed participation in the energy market, again, through that production cost model, in order to verify that the results are consistent. And if they're not, then we identify where the surrogate model challenges are, or where those mismatches are coming from. So let me give an example about a couple of those integrated energy systems that we're looking at as part of that conceptual design problem. And so just from a very high schematic view, you've got potential generators, and they could potentially make hydrogen or potentially make electricity. So here are your potential generators. They can directly make power. They could also use that power to make hydrogen, or use hydrogen potentially to make more electricity. That hydrogen could also go into a natural gas pipeline, or that hydrogen could go to hydrogen users or transportation. And so the big question that kind of comes up is, as the generator, what do you do with the power? The grid's asking, what are the electricity prices going to be? What power is going to be available? The fuel cell or the electrolyzer is trying to figure out, what should it do? Should it be making electricity? Should it be making hydrogen? And what is the interaction of all these different parts and pieces? What's the value of hydrogen for power generation versus the value of hydrogen for chemicals production or for transportation? So within dispatches, we've got 4 different case studies that we're looking at. One where we've got a nuclear power plant, and so it can make electricity, or it could make hydrogen through a PEM electrolyzer, and that hydrogen could either go to the market, or it could be used in a turbine to provide power, depending upon what the price is of electricity at any given time. This may or may not be valuable. We're doing something very similar with renewables, where we have a wind farm with a battery as well as an electrolyzer option, and what's going to be the best choices in different markets. And in the fossil case study, we've got CO2 capture with that, and a number of options for thermal energy storage, or again, potentially hydrogen, and then a retrofit case that's just fossil with some thermal energy storage options. So, real briefly to give you an idea of some of the types of problems that we can solve. This is a simple version of the conceptual design of fossil with thermal energy storage, where we want to decrease the power production of the system and use some of that energy to charge a thermal energy storage system. And the question is, how do you design that thermal energy storage? Where do you actually take power or energy out of the system? Where do you put the heat back in? And with different technology options for that energy storage, which one do you choose? And so we implemented this in IDEAS, solved it as a GDP, and we're able to solve the problem in about 10 minutes to determine the optimal charging and discharging profile for this particular system, which we then verified through dynamic simulation and utilized some of that nonlinear model predictive control to look ahead and actually understand the dynamics of the operating system. One of the other examples that I'd like to touch on is the design of flexible carbon capture systems. So how do you actually incorporate that flexibility in design in the design decisions? And so this is part of an ARPA-E project that's specifically around the design of flexible carbon capture systems, where we're given a LMP signals, LMPs being those localized marginal prices for price of electricity at different times of day. And we have a number of different scenarios that we're looking at. So we can't necessarily simulate over a full year period or use that for the design purposes. So we actually look at developing representative days. And what we're trying to do is maximize the net present value as a function of some of the revenue that we might get from selling electricity minus the capital cost minus the operating cost. And so looking at optimal power schedule, this is the LMP divided or the operating cost. So LMPs are fairly high, and they drop, and then they go back up. So in this case, the amount of power we want to generate significant amount of power when the price is high, and we want to drop down and basically shut down the system when the price of power is low and we can't recover our operating costs. And as the price goes up, we want to ramp up. So that translates to the capture system is, we want to capture a significant amount of CO2. And this is happens to be based upon a $150 carbon tax scenario. And then we don't want to capture anything more because the process has gone down. And then we want to ramp back up and capture as much CO2 as possible. And so as you think about different scenarios within different regions, the question becomes, do we build the carbon capture system or not? Which is going to give us the highest NPV. And as we look across different ISOs, for this one specific case study based upon a price taker assumption for different LMPs that were projected. So this was a synthetic data set from looking out to 2035. What would you want to do? And in many cases, the NP, red cases with an X on them, that means that you would actually be further ahead just paying the carbon tax at $150 a ton. And that was case one. Case two, we said, what would the NPV be if you had to build the capture system instead of comparing build it or don't build it? So we got rid of that discrete decision. And in many cases, the NPV is almost as high in those cases, even in those cases like CAISO, where you didn't want to build it. And then what would happen if you reduce that CapEx and OpEx? And in almost every case, if you could reduce the capital and operating expense compared to this very specific scenario, then you would be further ahead building the capture system and operating in a very specific flexible operation manner. So this is just an example of what you can do by integrating these types of models. And then the fourth one here in the multi-scale optimization is a quick look at expansion planning, specifically the co-optimization of investment over a long time period, plus then bringing in more aspects of operations in order to make those decisions. And so in expansion planning, the input is what investments are possible, what are the operational aspects of those, what are the transmission costs, and what's going to happen with demand, and what are representative profiles of the different sources. The model then looks at, in this case, it looks at different regions and transportation of electricity or transmission of electricity across those different regions for those different energy sources. And the output are what generators are going to be built in what year and what capacity, and what generators are going to retire over time, and gives an idea of approximate power flows and approximate generation schedules. So in one case, we looked at this, and if you look at the upper left hand here, we had a case with no carbon tax and one with a carbon tax. And over time, what you see is the number of flexible units, which are plotted here, actually goes down when you start having the carbon tax, which seems somewhat counterintuitive because flexible units, things like combustion turbines, where you can have really rapid turn on and turn off at very low capital cost, or reciprocating engines, you might expect that you might want more of those as the amount of renewables builds out. And digging into this, it turns out it's an artifact of how we use representative days in order to understand what's going to be happening in the future. And this is illustrated over here in the lower right, where the red line sort of shows what's happening, in this case for wind availability, wind capacity factor at any given hour. If you use kind of an average as a representative day, as opposed to taking into account some of these scenarios that have very high ramps from very high levels to low levels, and similarly, some of these scenarios with very low levels. And so if you actually go back and rethink how you include representative days, then as you look at system capacity, dispatchable units, which would be anything that you can just turn on and you have power. So that could be natural gas, could be a combined cycle, it could be a gas turbine, could be nuclear, compared with renewables. Going out over time for a couple of different scenarios, if we add these what are called lazy constraints, and you'll see that the amount of overall system capacity actually starts to go up. And although there's still a decrease initially in dispatchable units, those actually start to increase over time. And the amount of renewables actually doesn't increase quite as much. And sort of pulling apart that dispatchable units, what we see is that it's actually made up primarily of highly flexible units to kind of fill the gap that have low capital costs. And the point of this is that being able to capture those details is really critical when you're making long-term planning decisions as we're thinking about achieving these 2035 and 2050 goals. It's really important to make sure that we've got the details right in the model and we're capturing enough of those variabilities that we're making good decisions. And really, we can only add that level of complexity if we've got the right underlying computational framework that can actually handle those really large problems. So last example is scaling up and deploying new technologies, because all of these transitions of both the 2035 decarbonization of the electricity grid and 2050 goals are going to require lots and lots of new technology. So thinking about deploying that, this is one example from the carbon capture space, where this is a representation of a solvent-based capture system with an absorber and a stripper. And as we design that and try to scale that up, there's a lot of uncertainty. There's uncertainty in a large number of variables, both within the technology itself, as well as uncertainties within how that might operate. And so if you try to optimize the design, in this case, as an example, just from a deterministic standpoint, and you optimize at the green triangle space, which is explicitly feasible and optimal, but the ellipsoid represents the uncertain space, then within that ellipsoid, there are some operating regions that are feasible, as represented by the blue dots. But in the red dots, you won't actually be able to achieve the performance that the technology is supposed to achieve. And so a way around that is to use robust design, where we take into account that uncertainty during the design and optimization process, in which case then we can guarantee feasibility within this uncertain region, but there's a cost. In this case, the cost is fairly significant. So you can either use this information to design the system more robustly and scale it up, or you can take this information and look at what is essentially the price of robustness to help answer the question, should I do more testing in order to reduce my uncertain space? Is that going to be more cost effective? In which case my design might not have to be as robust. Or should I go ahead and build this and just recognize that it's going to cost more? And at what point do you stop trying to reduce uncertainty and you just go with the robust design? And that's somewhat illustrated here with the second stage costs in orange, where initially this might be the second stage costs given the uncertainty level, and you do some additional experiments and you're able to reduce that cost. So in summary, I talked some about some of the trends requiring innovation in decision support tools. I talked about the need for advanced optimization-based modeling platform, and made the point that IDEAS is trying to address those needs. And I tried to give 5 examples of where we're using the IDEAS optimization approach to address some of those challenges within that first bullet. And with that, I'd like to acknowledge support. Most of the funding for this comes from the Office of Fossil Energy and Carbon Management, specifically through the Simulation-Based Engineering Research Program. And this is the long list of all my collaborators. And I'd be very happy to answer any questions in the time that remains.